Section 3.4, we're going to encounter graphs of polynomial functions. Just a real quick listing of things that we're going to talk about today, and then we'll expand on this list. Some basic keys to graphing are to look for symmetry. That's step one. I'll talk about how to do that. Step two, to find zeros and multiplicities. We've done a lot of that already, so that's not new information. Step three, to determine end behavior. We haven't talked about end behavior at all. End behavior just talks about what happens on the edges of the graph. And in particular, what we're talking about is, do they both point upward, right? Do the arms extend up? Do they both point downward, or is there like one up and one down? And if so, does it look like one up on the left or one up on the right? Okay, so that's what we're going to be looking at, and I'll show you how we make those determinations. Steps 4 and 5 aren't really steps. They're more like guidelines to getting your graph to look reasonable. So you plot additional points if necessary, and the reason I say if necessary is because sometimes it's not necessary. All right? Oftentimes, you'll have enough information already to connect the dots and make sense of it, but not always. And then step 5 is to graph a smooth curve. So imagine you're doing connect the dots. So we're all kind of aware that when you do connect the dots, if you connect them all with these straight line segments, it ends up looking like a very boxy horse, right? But if you connect it smoothly, the horse actually looks more like a real horse. So we're going to be connecting things smoothly as we're working with polynomials. So let me talk about each of these in a little more depth. The symmetry one we haven't talked about before in this class either, although if you've had me for intermediate algebra, we did cross paths with this at that point. There's two types of symmetry for functions. One type of symmetry is y-axis symmetry, or even. It means that the left-hand side of the graph matches the right-hand side of the graph. They're mirror images. If you were to fold along the y-axis, they would line up perfectly. So visually speaking, for y-axis symmetry, a really good graph to sort of have in your mind is the graph of a parabola. Okay? It's a beautiful picture of this wonderful relationship here. Odd actually means that if you were to spin the graph 180 degrees, it would land back on itself. So an imagery to have in mind for an odd graph, so this one was y equal x squared, is our graph of y equal x cubed. And that graph actually looks like this, if you'll remember. And if you were to spin it 180 degrees, this arch that's going upward would now then be going downward, and vice versa. It would land right back down on top of itself. So this is sort of our classic odd image to have in mind. So that's a graphical perspective. Graphs are great for visual purposes, but sometimes they can be a little bit elusive. They don't actually give you enough information to know for sure. It just looks like it might be. So there's a more concrete way of determining this, and that's going to be algebraically. It's not a very hard algebraic step. What we're actually going to do is we're going to take our function and we're going to replace it with a negative x. So all the x's become negative x. So this is the test for even or odd. If the graph is even, then the function doesn't change. It will look exactly the same as it did when you had x in there, as when you have negative x in there. If the function is odd, it will look like you have changed all, not just some, but all of the signs when you've simplified. And I'm going to use these same examples, x cubed and x squared, to show you what they look like algebraically, because they're so nice. So if I were to take this one and I were to find f of negative x, it would mean I would replace the x with a negative inside. But what happens when I multiply negative x times negative x? Yeah, it becomes a positive, right? Negative times a negative is a positive. So I end up with x squared. But this is the same as I started with. It was my original function. None of the signs changed. That's what happens when you have an even function. None of the signs change by doing this. If you have an odd function, like this one, and you replace the x with negative x, now you actually have negative x times negative x times negative x. There's 3 negatives. So what happens when you multiply 3 negatives together? It stays negative, right? Yeah. So this is still a negative, and then now the x is cubed, and if you compare this to the original equation, it's the opposite. All the signs, not that there were very many because this is a simple equation, but all the signs changed. So you have 2 options. Either all the signs stay, well, there are actually 3. Either all the signs stay the same, that's even. All the signs change, that's odd. And if neither of those things happen, some combination of them, it's neither. That's our last thing. It means it has no symmetry, at least in terms of these 2 types of symmetry. It's not even, it's not odd. Okay, so I mentioned a little bit about multiplicities in the last section, but let me actually reiterate it here again in section 3.4. Your x-intercept behavior is directly related to multiplicities. So if you've got a root or an x-intercept, root, x-intercept, 0, they all mean the same thing. If you've got a number where it crosses the x-axis and it has a multiplicity of k, there's 2 options. The number k is either even or odd. If the number k is odd, it will cut through the x-axis. If the number k is even, then it will bounce off the x-axis. Okay, the last thing to actually write notes on is end behavior. Okay, so for end behavior is all related to or all about the leading coefficient test. So you first have to determine the leading coefficient. So this is something that you would have learned about or talked about in an intermediate algebra course. Your leading coefficient is the coefficient on the highest degree term. So your highest degree term is either got an even or an odd exponent. So if it's odd for your degree, you're on this line, the first line. And if it's even for your degree, you're on the second line. Okay, so it's either even or odd. The number, the coefficient itself, is either positive or negative. So I'm going to be flipping back and forth between this slide and the previous one I drew, so just bear with me as you're writing your notes. We're going to talk about the first one, the degree is odd. This one, the degree was odd, right? So this is the picture I want you to notice. On this picture, the graph has one arm, one edge of my graph going upward and one edge going downward. And this is the image when it's positive. It goes up on the right, down on the left. And if it's negative, it flips. It goes up on the left and down on the right.
So if it's even?
Nope, we're looking at odd. Yeah. So this was our sort of classic odd case. So over here, if it's odd and it's positive, it is down on the left and it's up on the right. That's what the edges, the ends of the graph look like. And if it's negative, it flips. It will go up on the left and down on the right. second line is what happens when it's even. So the first line, a good sort of picture to have in your mind is the graph of x cubed. A good picture to have in your mind of when it's even is the graph of x squared. So on x squared, or any even power, my images are like parabolas. Either they both point upward, or the edges both point downward. Okay? So if the value is positive, right, like it is on this one, it's positive x squared. They both went upward. So it goes up on the left and up on the right. If the graph had been negative, the parabola would have been opening downward, which would mean it would be pointing down on the left and down on the right. The end behavior and the multiplicities tell us how we connect dots. It tells us whether the edges go up or down. It tells us whether we bounce or cut through the graph. And those are really important pieces of information for us to have sort of placed in the right order. Okay, so are you guys ready to do an example? Okay, let's see a couple of examples that we'll get to today for these. Basically, we go through steps 1, 2, 3, and then we look at that and say, do I have enough information here to connect all the dots and do so in a way that makes sense? And if the answer is yes, we do it. And if the answer is not, then we add additional points, okay? And then we always do step 5, which is just to connect things smoothly together. So we're going to look at symmetry first. Symmetry is step 1. Some of your questions may specifically just ask you to decide about symmetry, right? But it is part of deciding about the graph as well. So what we do to test symmetry is that we use that negative x in place of the x's. So I take my x cubed, and it's now negative x cubed. And I take my x squared, and it's now negative x quantity squared. And I take my x, and it's another negative x. And I have my number 1 that doesn't change. We've done a couple of these already, or at least we've talked about them on the previous slides. What happens when I take negative x times itself 3 times? I think it stays negative, right? So this will be a negative, and it'll be negative x cubed. Now, this negative comes down automatically. What happens when I have negative x squared? It's positive, you're right. So that negative x squared that's in parentheses right there gets replaced for the positive x squared. The negative that's in front of it came from the equation itself, not from changing the signs by the negative x part. Over here I have a negative times a negative, right? So these are going to change into a positive x. And the last one's a positive 1. So I want to examine the signs. 3 options. They all stayed the same. They all changed, or there was some of both going on. What happened? Some of both. Some of the signs are the same. Some of the signs are different. So it's neither. This does not have either of those types of symmetry, even or odd. It's sort of the height of unhelpful. We did all that work to find that it's unusable. I mean, really. All right, step 2 is about our roots. So we attempt to factor. We might use a quadratic formula. We might need to use synthetic division, all sorts of things that we could use. Factoring is usually our best place to start. As I'm looking at this, it has 4 terms. 4 terms, if it factors, would factor by grouping, right? So we're going to attempt to group the pieces together. If I group these pieces together, what will come out of them? X squared. And I'll be left with x minus 1. Now grouping these 2 pieces at the end together, they don't have any value, so to speak, that will come out of them. But you could pull out a positive 1 or a negative 1 as necessary. And we need a negative 1 to come out because right now the signs don't match. Right now I have in here a negative x and a positive 1. But over here, I have a positive x and a negative 1. So if I take a negative out, it will change the negative x into positive x and the positive 1 into negative 1. And therefore, it will match the other one. So if I get to this point where these match, it means that factoring by grouping works. So if it works, then I can take that x minus 1 out. And I have x squared minus 1 from here and here left in parentheses equals 0. At this point, we can set each equal to 0. So this is x minus 1 equals 0. This is x squared minus 1 equals 0. Another possibility is you could factor the x squared minus 1 if you wished. It's a difference of squares, so it certainly factors as well. But I want to show you this from this perspective. So I add my 1. This is x is equal to 1. Here, when I add my 1, I get x squared is equal to 1. What do I get when I take the square root? Yeah, it's plus or minus 1, and I'm going to list them separately because I want to show you that I actually have a duplicate 0 here. X equals 1 shows up twice. If I had factored this, you would have seen that we had x minus 1, and x plus 1. X minus 1 would show up twice. So x equals 1 would be duplicated. Why does it matter? Well, it matters because that means that it has a multiplicity of 2. It's going to be a bouncing piece instead of a crossing through piece. But the x equal 1 has a multiplicity of 1. So in terms of my graph, x equal 1 and x equal negative 1 are both points on my graph, like this. One of them I'm bouncing through, and the other I'm bouncing off, and the other one I'm cutting through. Now our last thing to find or to talk about is end behavior. End behavior has everything to do with the highest degreed term. It's odd, right? It's odd and it's positive. So if you're thinking about this chart as your reference point, odd and positive is the first box right here. It's up on the left, down on the left, up on the right. So I'm just going to jot that down. It's down on the left and up on the right. So I may have to redraw a little bit, but basically here's what I know. It's going up here and down here. What happens at negative 1? Does it cut through or does it bounce off? It's cutting through, so it goes clean through right here. What happens at 1? It bounces off, so it will connect something like this. And if yours doesn't look smooth, once you connect them, just erase and redraw so that things connect and look smooth. I don't need any additional points to do this one. The end behavior and then the bouncing and the cutting were enough. And if you look at it, you should be able to look at this and say, yeah, it's not even, right? It's not a reflection across the y-axis. And it's not odd. If I spin this around 180 degrees, I don't end up with the same graph. Any questions on this one? Okay, we're going to do one more, and that's what we will end with today. This one is, the equation is negative x squared plus x, or negative x to the fourth plus x squared plus 12. So we're going to start out with symmetry. We're always going to do that. So for my symmetry, I want to try g of negative x. So here's a negative. Now I have negative x to the fourth. I have a positive. I have negative x squared. And I have plus 12. So this first negative will stay because it's part of the equation. What is negative x to the fourth? That is to say, is it positive or negative? It's positive. And the power is 4. The next one, there's an addition sign, so I'm going to bring that down. Negative x squared, positive or negative? Positive x squared. And then my constants are always the same. They don't have anything to change them. Did the signs all stay the same? All change? Or is there some of both? All the same. It is identical to what I started with. These signs and these signs all match. What that means is that the graph is even. It will have some sort of symmetry like a parabola. Now, it's important to note, and let me just sketch for you, that while a parabola has symmetry, not that one, but you know what I mean, that's great. There are other shapes that do too. Like I could have a shape like this if I were drawing it well that would have symmetry that's even, okay? So it's not just parabolas that look like symmetric around the y-axis, but they do. My roots is next. If you want to use synthetic division for this, you most certainly can. You can look at the ending value, the beginning value, take a test point and so forth and try it. That will be perfectly fine. This one actually factors pretty nicely. While it is not quadratic, it is similar to a quadratic, which we've encountered before, but it's been a while, so I'd like to show you again how that works. Notice that it starts out with a negative x to the fourth. It's never friendly to graph or to solve something that has a negative in it at the beginning. So my first recommendation is that let's divide everything by -1. That gives me x to the fourth minus x squared and minus 12. So while I have more negatives involved, I don't have a negative at the beginning. So if you'll remember what we did when we factored these is we said, okay, it's still a trinomial. I have x to the fourth, though, instead of x squared. So x squared and x squared would multiply to give me x to the fourth, right? So that's the one I would have. My signs need to be opposite because the sign at the end is negative, so I need one negative and one positive. I need two numbers that multiply to 12. I'm sorry, multiply to -12 and add to -1. -4 and +3. Very good. If you want to use difference of squares to factor this, you can. This would be x minus 2, x plus 2. I'll do that this way this time since I didn't do it that way last time. The reason I'm not going to factor the x squared minus or plus 3 is because it's not a difference of squares, right? It's a sum. There's an addition sign between it. That's not helpful. I can't factor that in a real number system, so I'll have to just go with my square root principle on that one. As I'm working through this, then I have x minus 2 equals 0, x plus 2 equals 0, and x squared plus 3 equals 0. So this one will give me x equal to 2, and this one will give me x equal to -2. Over here, I get x squared equals -3, and as I square root, I get imaginary values showing up. Because I put the square root on, I have a plus or minus. Because there's a negative underneath the radical, I have an I, and there's a square root of 3. Now, I need to find all the zeros, which I did, but the reality is that this set right over here doesn't show up on a graph because I'm looking at the real number line graph, right? It's a graph in the real number system, the Cartesian plane is. So those values, the I square root 3 and the negative I square root 3 won't show up on my graph. Only these will. So I'm going to plot these on my graph. I have -2 and +2. And it's important to notice that they are both multiplicity of 1. Did you guys notice that? So it's going to cut through the graph at both of those places. The last piece of information that I need to attend to is the end behavior. All right. Does this graph have a highest degree term that's even or odd? Even. And you make that decision based upon the largest exponent. It's even. It's even and negative. So where are we on this chart of things if it is even and negative? Yeah, it's down on the left and the right. So over here on my graph, I should be drawing it down on the left and down on the right. And it's cutting through as well. Now, it's tempting to think, and it may be true, that this is just a parabola, right? That's a possibility. But it also could have something else funky going on, right? Like that or something. So we need some additional points to try to get some kind of perspective of this. So what I'm going to suggest is to do the additional points at -1, 0, and 1. So let's actually evaluate our function at -1, 0, and 1. And actually, the cool thing is that -1 and 1 will be the same because the graph's even. So they have to be the same. 0 is the easiest one because if I put 0 in, everything cancels out but the 12. So that's 12. If I put in a 1, let's see, if I put in 1, I have -1 to the 4th plus 1 squared plus 12. So I think these cancel, right? This will be a -1, this will be a +1, so it'll also be a 12. So that's interesting. And if it's a mirror image, then this too is a 12. So what does that mean? Well, here's a 12, roughly speaking up here. It has to hit 12 here, here, and here. And it has to connect to all of them. So what does that mean? Well, it means that it has to pass through and come back down and do it again over here. Right? Because it has to hit all three of those points. It's definitely not possible to do this because that's not smooth, right? They have to be connected smoothly. So the only way to connect them smoothly is for them to have this sort of a mountain-like feature in between there. It's an interesting graph, right? It's very different looking. All right, we have 2 more examples. We'll pick up on those next time. Have a wonderful week.